So in class today, we didn't get a chance to answer C4, or what is the mole ratio of methanol and water that is contained only in the water vapor. So we did the work to find out that the mole ratio for water and methanol is 0.640 for water and 0.360 for methanol, and our mixture that's 50-50% by mass. So that tells us that even though those mixtures, those two components may have the same amount of mass, in terms of moles, they have different amounts, which makes sense because they have different molecular weights or molar masses. So the question we didn't get into was, okay, how do we figure out how to determine the mole ratio of moles that are only in vapor? Because we know that overall there are more moles of H2O, but we do also know that methanol has a vapor pressure of 4.69 kilopascals in this mixture, whereas water has 1.49 kilopascals. So even though we have a larger mole ratio overall for water, we have a larger vapor pressure for methanol. And so that begs the question is, what are the mole ratios and relative amounts of moles for these in vapor? And is the distribution or the ratio of the moles only in the vapor going to be different than overall? And spoiler alert, it will be. So the question then is, how would we go about setting up this problem? So we can make our math easy and assume we only have 1 liter, so things will cancel out nicely. But if we use our equation for working with gases, PV equals nRT, we know the vapor pressure for each of those gases. We're given the T, which in this case is 20 degrees Celsius, or 293 Kelvin. We assume a volume of 1 liter. We can pull R out of a table, so this allows us for each vapor pressure, for each individual component of our mixture, we can go through and solve through our number of moles or N. So for H2O, so for the number of moles of H2O, what we would do is we would plug in 1.49 kilopascals. We'd multiply this value by a liter. We divide it by our R, which in this case would be 8.314 liters times kilopascals over moles Kelvin. And then our temperature, which would be 293 Kelvin. And this would give us a value of 0.0000612 moles. Okay, so that's for our moles of water. Now let's solve for our moles of methanol. Our moles of methanol would be equal to 4.69 kilopascals times 1 liter divided by 8.314 liters kilopascals over moles Kelvin times 293 Kelvin, and that would give us a value of 0.00193 moles. Okay, so we can see here right off the bat there's almost an order of magnitude difference between our moles of methanol and our moles of water. So even though spread out between our liquid and our water, we have more moles of water total, it turns out that if we just consider the vapor, because the vapor pressure of methanol is higher, there's going to be more moles of methanol in the vapor than there will be water. But let's take a minute to calculate those mole ratios. And so if we calculate the mole ratios coming from those two values of moles only in the vapor, we get a value of 0.241 for water and 0.759 for methanol.